So to review a little bit from last time, we looked at A dotted with A, and we came up with our representation of our vectors and the components. We said that we could call one of them AI, E hat I, using our implied summation notation. Then we can dot that with another vector A, represented by the dummy index J, AJ, E hat J. We went through and we pulled the scalars out, the A sub I and the A sub J. We were left with E hat I dotted with E hat J, which we replaced with the Kronecker delta symbol. And again, as a review, the Kronecker delta is equal to 1 if the subscripts are equal, and it's equal to 0 if the subscripts on that particular Kronecker delta are not equal to each other. So for example, Kronecker delta 1, 1 would be equal to 1, Kronecker delta 1, 2 would be equal to 0. Alright, well in the end, we were able to show that this evaluated out to be A1 plus A2 plus A3. And if we look at this in a little bit more detail, well, this itself is a summation, whatever index we want to use. Maybe it's a summation of AI from 1 to 3. Or if we use our implied summation notation, we can rewrite this as A sub I. Alright, so this is kind of interesting. Let's change colors here to emphasize this. AJ Kronecker delta IJ is going to be equal to AI. And so what we've done then is kind of mechanically, if we evaluated out this double summation, we end up with this single summation. Mechanically, whenever we see a Kronecker delta appearing in an expression where that expression contains a subscript that's part of a summation in the Kronecker delta term and in another part of the term, the Kronecker delta can act as a replacement operator on indices. Okay. Again, it must have a common term. Okay. Let's see, how should I write this? The index to be replaced must be in the Kronecker delta and in the expression as a dummy or repeated index. Right, so AJ, we see that the I is here and here, and the J is there and there. In this case, we are free to choose either one we want. So we can write this as, let's write this down, AJ, Kronecker delta IJ. Mechanically, the Kronecker delta disappears, and we can replace the J in this expression, the second A, with the I. Alternatively, since in this particular expression the J is also repeated, we can replace the index J, replace the I with the J. Now we know with our implied summation notation with our dummy indices that AI AI is the same as AJ. So these are equivalent. If we had an expression that didn't have two repeated indices, so maybe it was like A, I, C, K, Kronecker delta, I, J, then what we could do is we can only replace the one that's repeated. So here the I is repeated in those two terms, so I can replace this with A, J, okay, this one right here goes into that spot, and then C, K. Now for one of your homework assignments, what I'm going to have you do is to go through a few different cases and show that this really does work out this way. But for now, just kind of keep in mind that Kronecker delta can act as a replacement operator on indices. Alright, so now that we've worked with our dot product a little bit, and we're gonna dive a little deeper into some things that can come out of our definition of our dot product, and we'll try to use this index notation more and more. So let's take a look at something called direction cosines. Our definition of our dot product of two vectors, A and B, was defined such that we had the magnitude of A times the magnitude of B times the cosine of the angle in between. Right, so that's our general definition for our dot product. Now, to get a direction cosine, what we can do is we can take the vector A and dot it with one of our unit basis vectors. Now, if I do the subscript I like this, that means that I is a free index. It could be E hat 1, E hat 2, or E hat 3. And so what this would be then would be the length of the projection of A onto E hat I, because the length of E hat I, our unit basis vector, is equal to 1. So we can say this would be the magnitude of A, the magnitude of E hat I, and then the cosine of the angle in between. Right now, we also know that if we picked a specific E hat I, say E hat 1, then A projected on to that particular unit basis direction would be equal to that component of that vector AX. Now, if this is the vector I, and this is the cosine and the angle between that particular one, we might want to specify that this could be a variable as well. This might be cosine theta sub I. Right, so let's go ahead and write this down again. We could say A dotted with E hat I is equal to the magnitude of A, the magnitude of E hat I, whichever one that was, times the cosine of that particular angle, subscript I. So if it's cosine, if we're looking at the one direction, it'd be E hat 1 and cosine theta 1. If we're looking at the two direction, that's cosine theta 2 and E hat 2. Now there's a problem here with this kind of notation right now, is that I have a repeated index, but I'm really trying to show that those are both free indices. Okay, so there's a way to handle this situation where we have a repeated index and we do not want a summation. Remember, if we see a repeated index, that ordinarily means an implied summation. Okay, let's go ahead and write that down too. Repeated index means an implied summation. But we don't really want that in this particular case. So what we're going to do is we're going to write off to the side no summation. And that way we don't have that implied summation. Okay, so that's how that case can be handled. So if we continue on with this free index type notation with no summation, the magnitude of A is the magnitude of A. The magnitude of any particular orthonormal unit basis direction is 1. And then the cosine of the angle in between would be the angle in between the vector A and the x-axis or the y-axis or the z-axis. But we also know that it would be that particular component. So in general, if I take A dotted with E hat I know that I would get the A sub I component. So in general, what I can say down here is that this would be the A sub I component. If I wanted to solve for the cosine of the angle, cosine theta I, that would be equal to the ith component of that vector divided by the magnitude of that vector. And these are our typical direction cosines. Let me draw a sketch, and we'll write this in another way that may be a little bit more familiar. If we have our three-dimensional coordinate system, our orthonormal coordinate system, and here's maybe my x, my y, and my z-axis, and here are my unit basis vectors. Number 3, and I have some vector that is in here. It's going to look like it's going to be kind of in the zy plane at first, but really it's just out here in space somewhere. Okay, that's my vector A. And if I project that vector onto each of those three directions, I get my components, AX, AY, and AZ. Now the angle, see if I can find a different color, the angle from the x-axis to that vector, a lot of people call that alpha. We would call that in this notation theta 1. The angle from the y-axis to the vector is beta, or in our notation theta 2. And the angle from the z-axis all the way over to that vector A is gamma. Right. So another alternative notation that you may have seen previously would be the cosine of alpha is equal to AX divided by the magnitude of A. The cosine beta is equal to AY divided by the magnitude of A. And cosine gamma is equal to AZ divided by the magnitude of A. And that may be a little bit more familiar notation to you, but this all is the same thing. So this expression on top with the free index is free to take the value I of 1, 2, or 3, which could be cosine theta 1, cosine theta 2, cosine theta 3, is that respective component of the vector A divided by its magnitude. That gives us our direction cosines. Alright, well let's take a look at A dot A again. Now we said that A dot A would be the magnitude of A times the magnitude of A times the cosine of the angle in between. And if there's 0 degrees in between, then this term goes to 1. So A dot A is the magnitude of that vector times the magnitude of that vector itself. We can also express this in terms of our components, like ax squared plus ay squared plus az squared. Well, we have an expression for our components. We can rearrange these, so we can say that any ai is equal to the magnitude of a times the cosine of the angle theta I. So we can rewrite this ax is equal to the magnitude of a times the cosine of the angle, or since it's ax squared, it's going to be equal to the magnitude squared times the cosine of theta 1, or alpha squared. And likewise, ay squared is the magnitude of a squared times cosine beta squared, and the last one, the magnitude of a squared times the cosine squared of gamma. So if we look at the left-hand side and we look at the right-hand side, we have a factor, well, that should be squared, we have a factor of the magnitude of a squared on both sides. We can get rid of it. And so we come up with our direction cosine relationship, cosine squared alpha plus cosine squared beta plus cosine squared gamma equal to 1. And that is probably a relationship that you're familiar with from other classes as well. So it's just kind of interesting how all this kind of falls out very naturally using our orthonormal basis, our representation in the definition of our dot product. Well, we have a few more things that we can define that we'll often run into. At this point, we've talked about a dot product. You may also be familiar with something called a cross product. So let's define that first geometrically, and then in terms of our, eventually in terms of our index notation. So sort of in a similar way that we've talked about our dot product, we'll define our cross product or our vector product in such a way that if we have two vectors and there's an angle theta in between, if we want to say that we want A crossed with B, the resulting vector is a vector that is perpendicular to the plane formed by A and B. Okay, so if I switch to a different color here, show this is C, and this is perpendicular to that plane formed by those two other vectors. Now, in a similar way that we define the magnitude of the dot product, we can also define the magnitude of the vector C. The magnitude of the vector C is equal to the magnitude of the vector A times the magnitude of the vector B times the sine of the angle in between. Now there are different ways to define vector products, and this way is a little bit clunky, but if we start with this definition, then we can advance into other things that we need to talk about. And so this is the definition that we'll take. Okay, the direction of C is perpendicular to the plane formed by A and B, and the magnitude of C is given by the magnitude of A, the magnitude of B, times the sine of the angle in between. There is a geometric interpretation of this. Okay. So if we look at A and B, let's look at it in the plane of A and B. So we have a vector A, and we have a vector B. If we were to extend this into a parallelogram, like so. If we were to look at this, the height right here of this parallelogram would be equal to the magnitude of b times the sine of the angle theta. In the area of the parallelogram, the total thing, would be the area of two triangles, 1/2 the base times the height and if we multiply that 2 through, the area of the parallelogram then would be the magnitude of A, the magnitude of B, times that sine of that angle in between. Right, so if we have two vectors and we do their cross product, we find the magnitude of the cross product. We have a vector that's formed perpendicular to that plane by A and B, but that length of that vector C happens to be the same as the area of a parallelogram that would be formed in the plane of A and B by those two vectors A and B. So we can kind of give that dimensionality, that relationship to a geometrical entity in that way. Well, this is going to give us rise to our next term that we're going to look at, which is the scalar triple product. And again, a term that you've probably heard of before, the scalar triple product, represents the volume of a parallelepiped formed by vectors A, B, and C. Now I'm going to sketch some vectors A, B, and C so we can kind of visualize this. And it's important to note that the vectors A, B, and C do not have to form a right-angled system. Now my vector C, if I call this one A and this one B and this one C, I've kind of drawn it so that C is pretty much perpendicular to A, the plane formed by A and B. That doesn't have to be the case. Any three vectors who are linearly independent, if you take their scalar triple product, you'll find the volume of that parallelepiped. So let me see if I can sketch the rest of this in 3D. And I got this one coming out here. It's my vector A again. Here's my vector B again. And if I can sketch the rest of these in. If I do the scalar triple product of those three vectors, A, B, and C, then what I'll get is the volume of that cube type shape or parallelepiped. Again, a cube would be at all right angles, but a parallelepiped may have a skew angle in there. Okay. The way we represent the scalar triple product of three vectors would be by taking vector A, crossing it with vector B, and then dotting that result with vector C. And depending on the sign of everything, how everything works out, that would be either a positive or negative number. So that represents plus or minus the volume of the three vectors A, B, and C. Now Now, one of the first things that we did when we talked about the dot product was we took a look at what would happen if we looked at the dot product of our unit basis vectors. Well, we can do something similar here. We can find out what happens if we take the scalar triple product of our unit basis vectors. So for example, if we had our unit basis vector e hat 1 and dotted with the unit basis vector e hat 2, across, e hat 1 crossed with e hat 2, and we dotted that with our third one, e hat 3, we'd be able to figure out what that would be. Well, e hat 1 crossed with e hat 2, it's perpendicular to the plane formed by 1 and 2, has a magnitude of 1. Well, that would be e hat 3. Of course, e hat 3 dotted with itself, the magnitude of e hat 3 is 1, so we have 1 times a cosine of 0 degrees. This would be end up giving us the value of 1. Right, so the scalar triple product of a set of unit orthonormal basis vectors is going to be 1. Now, it could be minus 1 if we did the reversed order of operations on the cross product. So e hat 2 crossed with e hat 1 dotted with e hat 3 would end up giving us minus 1. If we do e hat 2 crossed with e hat 1, we have a vector that points in the minus e hat 3 direction. And with that dot product, we still get 1, but now we have the minus sign, so we end up with 1. Okay. Some people would call this a volume orientation functional, and it helps us decide whether or not we have a left-handed or right-handed coordinate system. And if we wanted to, we could do these contortions with our right hand, with the right-hand rule and all of that. Volume orientation functional is a little bit more clean, but the right-hand rule still works. If we have a right-handed coordinate system and we cross the vectors a and b, if we take our thumb and take our fingers and curl it around in the direction from a to b, then our thumb would point in the direction of c. I will make a separate video where I demonstrate the right-hand rule with my own hand, and that will kind of help illustrate how that works. Now, the right-hand rule is probably something you've used in other classes, in undergraduate classes, for example, so I won't make a huge deal out of that. But the volume orientation functional is something that's kind of handy. Now, if we were to do a situation where we had some of these things repeat. So let's say we had e hat 1 crossed with e hat 2. I don't necessarily need the parentheses because the cross operation takes precedence. But if we do that and then we dot it with e hat 2, let's see what we might think we would come up with. E hat 1 crossed with e hat 2 is e hat 3. But e hat 3 dotted with e hat 2, well, those are perpendicular to each other, and so that's going to be equal to 0. Okay, so we have some different situations that can happen. If we take this set of unit basis vectors and do this operation, there's really 3 possibilities that we could get for any permutation of 1, 2, and 3 in this operation. We could either get +1, we could get -1, or we could get 0. This is going to introduce us to something called the permutation tensor. And we'll talk about that here on the next slide. Right. So in general, if we have 3 free indices and we have our set of unit basis vectors, we could have e hat I crossed with e hat j, and then dotted with e hat k. And I like to go ahead and put the parentheses in here just to make sure it's very clear what we're talking about. And this could equal to either 1, -1, or 0, depending on the values of I, j, and k. Now, just like the Kronecker delta, this kind of operation happens very frequently when we do this kind of analysis. And so we're going to represent this with a special symbol called the permutation tensor. It's epsilon I, j, k. And the way this is defined is I, j, k will be equal to +1 if we have what's called an even permutation of 1, 2, or 3. It's going to be equal to -1 if we have an odd permutation of 1, 2, and 3. And it's going to be equal to 0 if any index repeats. Now, I've used a name, and you may or may not have heard this name before. I just said this was a tensor. We're going to discover what tensors mean in a couple different ways. For now, just kind of go with that word, and we'll talk about it in a little bit more detail very soon. So the permutation tensor, let me write that name down. Epsilon I, j, k. A lot of times we're going to use the symbol epsilon for strain, but if it has 3 indices on it like this, that means it's a permutation tensor. So the permutation tensor epsilon I, j, k is equal to +1, -1, or 0, depending on whether we have an even or odd permutation of the subscripts 1, 2, and 3. So let's talk about even and odd permutations. So imagine I have these 3 numbers right here. If I were to go from 1 to 2, 2 to 3, and 3 to 1, this would be an even permutation. If I have my numbers here, 1, 2, and 3, and I were to traverse this circle in this direction, that would be what I would call an odd permutation. So if I have epsilon 1, 2, 3, that would equal to +1. But if I have epsilon 3, 2, 1, that would be an odd permutation. That would be equal to -1. And we can list all these down. So I start with 1 here. If I started with 2, that's 2, 3, 1. If I started with 3, that would be 3, 1, 2. All of these would be equal to +1. Good. And if I went the other way around, if I went 3, 2, 1, if I went 2, 1, 3, if I went 1, 3, 2, all of these would be odd permutations. Those would all be equal to -1. Of course, if any subscript repeats, then the value is 0. So one of the things, again, I'll have you do for your homework is I'm going to have you list out all the combinations for the permutation tensor, and I want you to see how many values you get, and I want you to see which ones are positive and which ones are negative by the definition of our scalar triple product of our unit orthonormal basis vectors. So, question I'll ask, and you can think about this for just a second, how many combinations will I have of 1, 2, and 3 for these free indices I, j, and k? I can have 27. So it's 3 subscripts, 3 indices, and they can all take on 3 values. So that's 3 to the 3. That would be 27 combinations. Okay, so that's a little bit to write out, but I want you to do it on that homework set because I want you to go through it the long way. Later on, we're going to take some shortcuts. There are ways that we can contract things when we have scalar triple products and Kronecker deltas, and we'll see some things that kind of come out of this through the use of index notation, but we can always go back and do it the long way with summations and so forth. Alright, well, now we talked about this permutation tensor. Let's go back and look at our scalar triple product of 3 vectors, and we can write this in terms of the representation of the vectors in our coordinate system. So again, vector A would be equal to A sub I, E hat sub I, and so forth. And let's see how the permutation tensor kind of naturally comes about through the use of our scalar triple product of 3 component 3 vectors anywhere. Alright, so here are our 3 vectors, A, B, and C. We're doing A cross B dotted with C. We talked about how we can represent vectors in our coordinate system. So we're going to substitute here AI, E hat I, and it's the same as A. And then we're going to cross this with B, J, E hat J. And then we're going to do a dot product with CK, the scalar components, times E hat K. Now, these 3 scalar components that we have right here can be brought out in front of all the vector operations. So we've got A, I, B, J, and C, K. All right. Now we have E hat I crossed with E hat J dotted with E hat K. Now we do have a triple summation because we have 3 pair of repeated indices. So there's an implied triple summation. We're still kind of getting used to this, so let me go ahead and write this down. I won't write that down all the time because once we get used to our index notation, we'll just know that whenever we have a repeated index, then we have a summation. Here we have 3 repeated indices, so we have 3 implied summations. All right, so what we have then is AI, BJ, CK, and now we have permutation tensor I, epsilon I, J, K. Now in a class like statics or something that you may have taken in an undergraduate class, you may have evaluated a scalar triple product by taking the determinant of the components of vectors. So we have like AX, AY, AZ, it should be B, X, BY, BZ, CX, CY, CZ, and you take that determinant and you get that number, and that determinant is the volume contained by those 3 vectors, assuming you have linear independence. If you can't find any volume, then 2 of your vectors at least are dependent on one another. They point in the same direction, they're parallel. All right. Well, again, for one of your homework problems, I'm going to have you evaluate using the determinant notation, and I'm going to have you evaluate using the index notation to see if you get the same result for the determinant. Now, there's different ways to find determinants. You might remember one way to do it is if you copy over these two rows and you go this way and you go this way and you find the result. Let's go ahead and do that just in case it's been a little while since you found the determinant. Linear algebra is just so neat, in my opinion. There's a lot of interesting things you can do with linear algebra, and there are a lot of interesting things related to continuum mechanics and linear algebra that just kind of pop out, especially when we're using the orthonormal basis system. Okay, so let's see if I remember how to do this. If I were to take this set coming down this way, and this set coming down this way, we can do this for a 3 by 3. And then this set coming down this way. And then we subtract all the other diagonals. A, Z, B, Y, C, X. A, X, B, Z, C, Y. And then A, Y, B, X, C, Z, and that would be the determinant of that matrix. Okay, so what I want you to do then is I want you to evaluate the triple summation of this. You're going to have 27 terms. A lot of them are going to go to 0. Some of the permutation symbols will go to +1. Some of the permutation symbols will go to -1. But what you should end up with in the end would be the exact same expression, except maybe you're going to be using A1, A2, and A3 instead of AX, AY, and AZ, and so forth. But you'll see that you'll get the same expression when you evaluate that with the index notation. Well, there's also a strong relationship here with the permutation tensor and just the cross product itself. So let's talk about that next. All right. So if we look at our want to look at the cross product again, we're going to start by what we just noticed about the scalar triple product of 3 vectors, A cross B dotted with C. And as we had broken it down before, we can use our representation of our vectors, AI, BJ. I'm going to bring those out in front together. And then we have E hat I crossed with E hat J. And then we have the result that's dotted with CK E hat K. Now when I do the cross with the E hat I crossed with E hat J, I will get the other direction. I will get a component of this in the other direction. It'll either be in the 3 direction if this is 1 and 2, or it'll be in the 2 direction if this is 3 and 1, and so forth. So what I'm going to say is that this results in a vector that would be in the K direction. You know, it's a free index, so it could be 1, 2, or 3. But when I do this dot product, and I dot it with the unit vector in the E hat K direction, the only thing that's going to survive that dot product will be the one that's not repeated. So it's a little bit clunky, but I'm going to say that this is in the E hat K direction. where the k in this case represents things that are not in the I or the j direction. And I have specific values for these indices here. Now I do have a summation. I do have a triple summation in this product. So if I want to define a cross product, then what I can do is, based on this triple product, I can just say that A cross B is going to end up with AIBJ permutation tensor epsilon ijk e hat k. Right? And again, it's only going to survive the dot product if one of these are not repeated. Okay. So take a look at that, see if you can convince yourself that that does work out for a dot product. And again, another thing you can do is maybe in a class like statics, you evaluated the cross product of two vectors by taking your unit basis vectors and doing these two vector components, finding their determinant. And this is kind of a weird way, I guess, because it's a determinant that results in a vector. And see if you can use this method to generate the same thing. So here we have a triple summation because we have repeated I, j, and k. So evaluate that result to check. In fact, so we did the cross product, or we did the determinant last time. Let's go ahead and evaluate this. Again, I won't do this all the time, but let's go ahead and write down the 27 terms that result from this. Let me start on a fresh page. Alright. We're going to do this. Again, I won't do this all the time. But we could start off with everything equal to 1. And then everything, then we can advance k. Now, as I write all these indices down, I will tell you it's very easy to make a mistake. And I will try not to make a mistake. A lot of times what happens is I start thinking about the next term while I'm writing down the current term, and then I'll mess something up. If I make a mistake, please leave a note for me, and I'll try to amend this lecture, or I will try to make some comment so that I can catch those mistakes. I guarantee I'll make a mistake somewhere, so keep a close eye on me, and I'll just do the best that I can. Alright, so everything's added together. So we did A is equal to 1, B is equal to 1, and we advanced K from 1, 2, and 3. So now maybe we can leave A is equal to 1, and we can make B is equal to 2, and then we can advance K. Alright, I think I'm alright so far. A1, B2, permutation tensor 1, 2, 3, E hat 3. And now I'm going to advance B. Alright. And now I'm going to advance A. So I'm going to have epsilon 2, 1, 1, e hat 1, and epsilon 2, 1, 2, and that should have been an epsilon right there. Two, 1, 3, e hat 3, and I'm going to pause the video. I'm just going to complete this. Like I said, I should end up with 27 different terms here, and let me complete this, and then I'll pause this, and then it'll pop up with everything turned in. Alright, so I went ahead and did all of that. Again, I'm not going to do this very often because we're going to use our index notation. Let's see if I have the right amount of terms. I get 3 across here. Should have 9 rows. 1, 2, 3, 4, 5, 6, 7, 8, 9. And a whole bunch of these terms are going to go to 0 because a permutation tensor goes to 0. So that's going to be a 0. It's going to be a 0 and a 0. That's repeated. There's a repeated. It's repeated. That's repeated. Repeated. All of these have repeated indices. So all of these terms go to 0. And I should end up with 6 terms that are not 0. Let's see if we can count those. 1, 2, 3, 4, 5, 6. And I missed one in red there. This one also is 0. Okay. And so some of those are even permutations and some of those are odd permutations. Again, this is going to be mainly a homework problem for you. But I want you to demonstrate that the vector product of A and B, the cross product, evaluates to be the same whether we use index notation or whether we use that kind of weird determinant thing to find out the new vector. Alright, so for your homework then, you're going to have some questions where I'm going to ask you to use a coordinate-free approach, which is a vector diagram type approach, and I'm going to have you do some problems where you use index notation. And we're mainly going to shy away from the vector approach, the vector diagram approach. It's useful in some contexts when you have a clear idea of the geometric interpretation of the problem. But after a while, you should get very comfortable with our index notation. Now, there's one last thing I want to talk about in this lecture, and that is that word tensor that we've used a couple times. We're still just a little bit away from formally defining tensors, and although we've not formally defined them yet, we've already seen 4 different types of tensors. Some of these you probably call something else. So a scalar, we can say, is a form of tensor. A scalar would be something like the magnitude of a vector, and we would call that a 0-order tensor. A vector, okay, like the vector A, would have components that would have 3 components that we would call a first-order tensor. We've talked about second-order tensor, the Kronecker delta. In component form, it actually has 9 components. Now we can identify this as a second order tensor because it has those 9 components. There's more to it than that, and we'll talk about that in just a little bit. But we can identify them as second order tensors without yet formally defining what a tensor is. And then we've taken a look at the permutation tensor, epsilon I, j, k, and that would have 27 components, and that would be a third order tensor. And in fact, the number of subscripts will identify the order, and if we want to know the components, let's write that down, subscripts identify the order. Just because it has subscripts, it may not be a tensor. There's other things, other properties it has to possess. But if you know it's a tensor, you can identify the order based on the number of subscripts. And then the components are given by 3 to the order. So a scalar is only one number. 3 to the 0 is 1. A vector has 3 components. 3 to the first power is 3. Second order tensor has 9 components, 3 to the second power. A third order tensor then has 27 components. And we will actually go up to fourth order in this class. We will look at something called the Elasticity Tensor. And so that would have 3 to the fourth power. In general, that would have 81 components. Okay, so there's a lot of things to keep track of. Our index notation will make life so much easier working with all these different components. While we're here and before we end this lecture, let's talk a little bit about representing vectors, tensors, and so forth on the next page. We can have these components, but we can look at these components in different groupings. Scalar is just a number, like the number a. We can say a vector, we know that we have the 3 components. We can group those in a column if we would like. A1, A2, and A3 would be the components of that vector. Second order tensor, like the vector B, or in components, it would be like Bij. We can represent that as a matrix. If we go to higher than second order, then you can kind of think of, instead of a matrix that's in 2 dimensions, you can think of a matrix that's like a cube. So we expand out in the 3rd dimension with the additional components so that we end up with 3 cubed, 3 components by 3 components by 3 components. Now, a fourth order tensor, that gets to be kind of difficult to visualize. But if we stick with our tensor math in our tensor algebra, we can do all the operations no matter what order that is. Okay, so we're going to let the math take care of the visualization. We don't have to do the visualization to n dimensions, but we can have n-dimensional tensors and deal with them in the same way that we deal with second order tensors. Now, some people will represent fourth order tensors as big matrices, and there are some symmetries that we can exploit to reduce the size of the matrices, but those matrices aren't necessarily tensors. They don't transform like tensors do. What we'll find out in a couple lectures from now, I think, will be that tensors are things that have certain transformation properties as we transform them from one coordinate system to another. We'll get into that later, but for now, just kind of keep in mind that we can represent second-order tensors very similar to the way that we represent matrices.